What's going on, everyone? Welcome back to Axiom. In today's video, we are tackling conflict serializability. And honestly, this is a game changer for your database management systems preparation. Pay close attention because this will definitely come up in your exams. Here we go. Modern databases process millions of transactions every second. At this scale, forcing every operation to wait in a single file line would bring the entire system to a halt. This schedule shows a baseline for safety, a serial schedule. Transaction 1 executes completely from start to finish before transaction 2 begins. The data is safe. But the system is slow. This concurrent schedule shows the alternative instructions are interleaved to maximize performance, but interleaving creates risk. Look at the exact point of failure. Transaction 2 reads account A in an intermediate state. The final sum is corrupted, destroying data integrity. This violation breaks a core requirement known as isolation. Isolation is an ACID property dictating that concurrent execution must yield the exact same database state as a strictly serial execution. ACID stands for atomicity, consistency, isolation, and durability. The four key guarantees of a reliable database transaction. To scale databases safely, we must find a mathematical method to prove that a fast interleaved schedule is logically equivalent to a safe serial one. We start by examining the environment. Multiple transactions attempting to access the exact same data item, which we will call variable q, in memory. We can establish rigid logical rules for how these accesses interact. First, two read operations on variable q do not conflict because neither alters the underlying data. However, a read and a write operation on variable q do conflict. The order of execution dictates the outcome because reading before the write retrieves a completely different value than reading after the write. Finally, two write operations conflict. The final state of the database depends entirely on which transaction writes last, overwriting the other. These rules give us a core theorem. If two consecutive instructions in a schedule do not conflict, their execution order can be reversed without changing the final result. Identifying these specific read and write conflicts is the absolute prerequisite for safe concurrency. It is the only way to know which parts of a schedule are locked in place and which are flexible. This concurrent schedule provides a starting point for analysis. We can see the interleaved layout of operations between two transactions. By examining specific instruction pairs, we can identify those that target completely different data items because they operate on separate variables, they do not conflict, and are candidates for swapping. We can systematically slide these non conflicting operations past each other. This logical movement allows us to uninterleave the transactions step by step. This layout shows the state of the transactions after a series of legal swaps. The instructions have been moved to eliminate the interleaving entirely. We call this state conflict equivalent because we transform the concurrent schedule into a serial like state using only legal swaps. The mathematical outcomes of both schedules remain identical. Manual swapping proves that a concurrent schedule can be safe, but it is computationally impossible to perform manual swaps for millions of transactions in real time. We need a scalable algorithmic approach. We abstract the tabular schedule into a precedence graph. This mathematical structure consists of a set of vertices represented here by transactions and a set of edges. Directed edges or arrows map the chronological dependencies caused by conflicts. If transaction 1 executes a write before transaction 2 executes a read on the same item, an arrow is drawn from T1 to T2. The same applies to the other conflicts, read before write and write before write. Each generates a specific directional edge. The direction of the arrow dictates the mandatory order of operations. It locks the transaction at the tail of the arrow into executing before the transaction at the head. A precedence graph strips away the noise of a massive schedule, leaving only a pure mathematical map of the mandatory chronological dependencies between transactions. Here is three different precedence graphs representing three distinct database schedules. A cycle detection algorithm scans these graphs to ensure no transaction paths loop back on themselves. This cycle graph contains a cycle. A cycle indicates a logical paradox. Transaction 1 must execute before transaction 2, but transaction 2 must also execute before transaction 1. This schedule is corrupted and cannot be serialized. The remaining graphs are directed as cyclographs or DAGs. A directed as cyclograph is a graph with directional flow, but no closed loops or cycles. This leads to the fundamental theorem of database concurrency. If and only if a schedule's precedence graph is a directed acyclic graph, The schedule is conflict serializable and the data is mathematically guaranteed to be safe. A verified DAG is then used to order operations. The system performs a topological sorting. Topological sorting is the process of flattening a directed graph into a valid linear execution order. But analyzing a graph after instructions are scheduled is a retrospective proof. Actual database engines require real time prevention. To achieve this, systems implement the two phase locking protocol or 2PL. Two-phase locking is a concurrency control method that requires transactions to acquire all necessary locks before releasing any, ensuring strict execution order by requiring transactions to acquire shared or exclusive locks before acting on a variable. The scheduler forces incomplete. Alright, that was conflict serializability explained from start to finish. If you found this useful, smash that like button and share this video with a friend who's also studying for exams. Subscribe to Axiom for more lectures like this, and I'll catch you in the next video. Take care.